Okay, Assalamualaikum class. Okay, for today we have the eigenvalues and eigenvectors. So this is the last topic or the last subtopic in your first chapter. Okay, alright, so let's look at the definition. Okay, we have here the definition. Okay, so the definition given here is, let E be an n times n matrix and we have a vector x be a non-zero column vector. Okay, so a number lambda, so this is your lambda, is called an eigenvalue. Okay, eigenvalue of A if Ax equals to lambda x. So this is the equations that we will use later on. Alright, and the column vector x, okay, so the x is corresponding to the eigenvalue lambda, it is called an eigenvector of A. Okay, so we have two things that will be involved in this topic, eigenvalues and eigenvectors. Okay, so firstly the equation that we will use is Ax equals to lambda x. Okay, so from this equation actually we will get a new equation, or we can write in the other form, that is, so if you simplify, next you will have Ax minus lambda x equals to 0, and then when you factorize it will be A minus lambda I x equals to 0. So remember, okay, the lambda here, okay, what is it? So the lambda here is a value, so it is a number or a constant. Alright, okay, so that's why, since this lambda is a constant, so when you want to minus, or when you want to subtract A with the lambda, so you need to put identity in your lambda. So it means a matrix minus with the matrix. Okay, so that's why we have this formula, A minus lambda I E x equals to 0. So this is the homogeneous system. So the homogeneous system that we will use to find the eigenvectors for the corresponding eigenvalues. Right? So remember, here we have eigenvector of A is not unique. So eigenvector, it is not unique. Okay, next let's continue. We have here the magnitude. Okay, so we have a magnitude. So the magnitude of a column vector x, okay, where the vector is will be equals to x1, x2 until xn, is defined by, so this one is magnitude of x equals to square root of x1 square plus x2 square plus dot 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 until xn square. So this is actually the formula of distance. Okay, if you can remember, it is actually the formula of distance. So this formula we will use later on in the next chapter of vector. Alright, okay, next, if x is an eigenvector corresponding to the eigenvalue lambda, okay, then the unit vector u equals to x over magnitude x. Okay, so this is the formula of unit vector. Right, so unit vector u is x over magnitude x. It is called as normal eigenvector. Okay, if the question asks you to find the normal eigenvector, then you need to find x divided by the magnitude x. Okay, so we have the note here. Remember, the normal eigenvector is unique. So normal eigenvector is unique. Alright. Okay, let's continue with the example. Okay, let's look at here. We have let the matrix A is 10, negative 18, 6 and negative 11. So it is a 2 by 2 matrix. So determine whether x1, so x1 here is the eigenvector. Okay, it refers to eigenvector 1. Okay, x1 is 2, 1, and x2, the eigenvector 2, is 3, 2, are eigenvectors for matrix A. Right, then find the corresponding eigenvalues. Okay, firstly, to solve this question, Remember, the formula that we will use for this question is ax equals to lambda x. So this is for the formula that we will use. Alright, so here for this question, it is given two eigenvectors, this one x1 and x2. So to determine whether these two are the eigenvectors for matrix A, so we will follow the formula. So we have here is ax, so your ax will be 10, negative 18, 6, negative 11 times with x. So let's say the first one we use is for ax1 equals to lambda x1. Okay, alright, so this one lambda 1 x1. Okay, so your x1 here is 2 and 1. Alright, so if you multiply, it will be this one. So we have here is the answer is 2, 1. Okay, so remember, to multiply you will use this cross multiply. Alright, okay, then your aim is you want to write in the form of lambda x, right? So in this case, if you write in the form of lambda x, it is actually equals to 1, okay, 1 times 2, 1. Okay, so here you will have this one is your first lambda, okay, corresponding to your first eigenvector. Okay, thus we say that, okay, lambda 1 equals to 1 is an eigenvalue of A with corresponding to the eigenvector x1 equals to 2, 1. So here, if we can see here, it is actually ax equals to lambda 1 for x1. So this one ax1 lah. Right? Okay, so similarly, we want to determine for the other eigenvector 3, 2. Okay, so we want to check for ax2, it should be equals to lambda 2 x2, right? Okay, so starts with ax2, it is 10, negative 18, 6, negative 11, and your x2 given there is 3, 2. Okay, so when you simplify, you will get it is the first one is negative 6 and the second row is negative 4. Alright, so your aim is we want to write in the form of lambda x, right? So if you write in the form of lambda x, meaning here you must have x, your x here is 3, 2. Okay, so this is your x2 and we want to know what is your lambda 2 here. Okay, so when you factorize negative 6, you will factorize 3, it will be negative 2, right? And also for 2 is also for negative 4 is also negative 2. So this is your lambda 2. Now we have in the form of ax2 equals to lambda 2 x2. Thus, we say that lambda 2 equals to negative 2 is an eigenvalue of A with corresponding eigenvector x2. x2 equals to 3, 2. Okay, so when you can use this kind of working, okay, or this kind of solution, it is when you are given, okay, so you are given the eigenvector. Okay, so you have the given the eigenvector and we want to find the eigenvalue or the lambda.